So my name is Josep Carreras. I'm the group leader of lighting. Our research institute is the same kind of network that IREC is. When you find this symbol here, this means that it's from the CERCA network. And we are located basically in Barcelona. We have a building in Barcelona near the Forum and another in Tarragona. This is a research institute about energy in all the senses. So we have a thermal energy and lighting group, which I'm leading. We have also an electrical engineering area, advanced materials for energy. This is the biggest area in our institute. We have the functional nanomaterials, nanoionics and fuel cells, hydrogen. We have also solar energy materials and systems, energy storage and energy harvesting, and materials and catalysis. This is from one side. In the other building in Tarragona, we have bioenergy and biofuels, and the laboratory for thermal energy. Okay. So this is a bit of our history. Our trustees are the government of Catalonia, two departments of the government of Catalonia. We have one ministry in the central government in Spain, 3 universities, the UB, the Rovira i Virgili, and the UPC. And finally, we have 6 companies as trustees. So we have to not only publish and make the government happy about our scientific results, but we have to have also the companies happy with the results. We have to make projects with them and with industrial value, okay? So the institute is divided into 2 main subjects, the long-term research, so basic things, fundamental things, but not too much, so that we can drive them to the technology development and finally reach to the marketplace, okay? We are also a member of the Keikino Energy. This is a platform or a network inside the European Institute of Technology. And this is about 29 companies, universities, trying to make the research reach the marketplace. So this is a good source of income to us. A few numbers, just to say that our main incomes come from European projects, 76%. We have also industrial projects, only 9%. We're trying to improve this, but in these times of crisis, it's a little bit difficult, at least here in Spain. And national projects finally is around 15%. So let's go to the main part of my presentation. This is a brief outline of the lighting technologies that we know today. We start with the candle, with the light bulb, which is not very efficient. I think these numbers are not very accurate because 4%, I think it's 2.6%. Then we went to the fluorescent and compact fluorescent lighting, which is the same, but with the shape of the E27 light bulb. And finally, these days we're arriving to the LED technologies with efficiencies higher than 100 lumens per watt and quite efficient. But up to here, all the market has been concentrated on being more efficient every time. Now, the current trends that we are finding are related more to the connectivity of lighting, to the fact that the light is digital due to the LEDs. Okay, so I'm going to speak a little bit about this after. So this is a very well-known graph. So this is how the market has been driven up to now. We are increasing the lumen output per LED, and we are decreasing the cost per lumen. So this is a perfect market in this moment. But my point here is that maybe if we have some numbers here about the maximum luminous efficacy, as the last speaker told us, my numbers is that we have a maximum in efficacy if we want to have light quality. This is around, depending on the color temperature, but we are around 300 lumens per watt. So this is our limit, and maybe it has not much sense to keep increasing efficiency if we are losing color quality. Okay, so this is a little bit of my point on the central point of my talk. So when we think of lighting, we think more of having a good quality lighting like this, but instead what we find in our offices or workspaces is something like this. It's a lighting that is not adapted and is not respectful with our health, our productivity, and so on. So we have also to think of getting into the market high CRI products with resemblance to natural light or the black body. And this is what is starting to being called human-centric lighting. So lighting that is focused on humans. And also all the integration with digital and monitoring capabilities of the lights, the energy consumption, and so on. And finally, the standardization is also a problem that we are fighting. In terms of the problems that we can tackle from the material side, we have the droop that was mentioned before. This is the mechanism by which the efficiency is decreased as we increase the current injected into the chip. So this was finally, it's some controversial, but finally it seems that is a non-radiative mechanism called a Auger mechanism, so that the more current you inject, then you are favoring the non-radiative processes in the chip, so you are losing efficiency. And this is a real challenge in the current LED technology. Then we have another problem that is related to the materials that we are using. We have quite efficient in both edges, but we have a gap which is known by the green gap, in which we don't have any efficient technology, and we have to use phosphors by down converting blue or ultraviolet light into white in this zone. Okay. And another big problem that we face is the light extraction. So we have to use extractors in order to get the light out of the chip, and not only of the chip but out of the luminaire. So these principles apply at the chip level and also at the diffuser elements and all the optics of the luminaire. Okay. So this is also a very limiting factor for lighting. Oops, sorry. So if we speak about light extraction, there are a lot of extractors based on photonic crystals and nanopattern surfaces that can help in getting the light out of the chip. And the expected efficiency is around, it can be improved from 25 to 40% by using these structures. So the strategies to make white light, I guess that you already know, but I will just mention very fast, is that we have two strategies. We can use a multi-chip, like combining different colors in order to match the white point in the black body locus, or we can use single chip devices with phosphors, okay? And these are taking the energy from a blue LED chip, and they are releasing, down converting by emitting a broader spectrum. Well, this is the principle of electroluminescence that you already know. In IREC, we are working in colloidal, basically. We have only aligning materials and lighting, and it's about colloidal quantum dot, basically with this material, cadmium selenide or sulfide. And what we can see is that we can create RGB components that are not perfectly efficient, but the numbers are improving day by day. So in the end, this can be a promising technology, but it's been quite a long time, and the results are not still there. Whoops. Okay, but the other part of the presentation that I would like to talk about is about this digital world that the LEDs can bring us. So what we already know is that they are efficient, they are durable, and they are environment friendly. But what is not so known is that they are easy to control, they are fast, and that there are a lot of narrow band opportunities in here. Okay. So another advantage is that they integrate very well with the current electronics and mobile phones and all these things. They can communicate, they can transmit information by pulsing because they are very fast. So this is what can enable the Wi-Fi communications. And that we can combine several LEDs, color LEDs, to tune the spectrum to our needs. This is also a great advantage. And there are people that is speaking into not converting, but adding to the consumer electronics the word consumer photonics. And this can be a reality thanks to the LEDs. There is another topic that is how light can affect to humans' productivity in offices environments, at work, etc. Let's imagine that I'm the manager of a company and that I have two options. I can change all my lighting so that it's super efficient. Let's say that I can save like a 50% in the electricity bill. Or my other option is just to search a little bit in the literature and see how can be, by which number can be improved the productivity of my workers by changing the light following a human-centric scheme. Okay. Attending to the most recent bibliography, it is said that 7.7% savings in productivity can be attained. This is a number that you can rely on or not, but is what the last studies are saying. So if I take the first option, my savings per year will be 450 euros, because I'm saving 50% of my energy. Lighting accounts more or less for the 20% of the energy consumption. But if instead of this, I'm using the second approach and I care about the lighting spectrum, so that, for example, I enrich the content of the spectrum with blue light so that the productivity can increase, and etc. Then, and attaining to this number, the savings for the same office are 23,000 euros per year. So this number is quite significant, and there's some that can be discussed here. Let me talk about a couple of projects that we have, European projects. The first is the HiLED project. Here we basically deal with light for health, light for horticulture, for growing plants, and light for museum lighting. Okay. So in health, no, sorry. I think it's a slide missing. Well, here the University of Newcastle is trying to find the best spectrum in order to improve mood and cognitive performance, okay, while minimizing the disruption to the sleep-wake cycle, because there are some studies as well that are claiming that light can interfere in the sleep patterns of humans, okay. So this first part of the project, we're trying to do some research in this regard. And the kind of luminaires that we're using, we have fabricated an LED matrix with all the wavelengths possible between 380 and 780, separated by 20 nanometers, something like this. Then we have created all the driving electronics and a microcontroller unit here that is in charge of have all the algorithms necessary to calculate the relative amplitudes of all these channels and can match every spectrum. So you can say, okay, now reproduce daylight. It reproduces more or less quite accurately the daylight that you can measure outside in outside spaces. So all these electronics has to be put somewhere. We just made a housing here with an integrated spectrometer in order to make sure that the intended spectrum is the one that you have. Well, this is we have patented this technology, and we have connected this device into the Internet of Things so that you can control with your mobile phone and so on. The other part of the project is related to horticulture. Here, this is the human sensitivity of the eye that peaks at 555 nanometers. But the plants have another biological process that is much different in order to get energy from the sun. And this is the sensitivity of this process. And it has a valley in more or less at the same region that our eye peaks. So the best light that you can give to a plant is in the infrared and in the blue part, okay? And we're studying whether or not green light has an effect on the, for example, on the creation of vitamin C and other components in the plants. The last application is museum lighting. Here we have, with this light engine, we have created different spectral properties so that we can reproduce all the pigments from the painters in the past. Okay, we have analyzed every pigment with a spectroradiometer, and then we have created the right spectrum in order to illuminate so that the color shifts are minimal. Okay, and we have installed this setup in the National Gallery with a painting of Paul Gauguin and a reproduction near, so that it can be easily seen how the difference emerged when you tune the different spectrum. And also there were like 20,000 people participating in all over the 4th month. So we got an interview and some results from all these people that we're going to publish now. No, this is nothing. The other project, this is a mistake, is not highlighted, is LED4R project. We were participating here, partnering with Osram. And this was quite impressive because we changed all the illumination in the Sistine Chapel. The Sistine Chapel has 25,000 visitors per day, which is quite a lot of people. And it has insufficient illuminance level. It had insufficient illuminance level on the floor, so that when people were entering into the chapel, the first thing that they found was a stair like this, and they were falling all the time, and it was not even safe. So not only we increased the illuminance levels on the floor, on the walls, so that we match the spectrum, so that the color differences were minimal. Okay, so in reality, what we did is tune the spectrum to the black body, so that the pigments and the paintings were seen as Michelangelo did in the past when he did his things. So basically, in museums we have energy. We have to take care about energy efficiency, color quality, because we want to see the artworks in a correct manner. And a third thing that is very important is art preservation. We don't want to damage the pigments of the paintings. So this, in this combination, we could find the right spectrum. This is a little bit the spectral measurements that we took. Is an example of a painting and all the points where we took measurements, and we did this for every fresco in the chapel. And finally, we built a spectrum with cool white, warm white, and 3 RGB channels. And we calculate this spectrum so that the color difference were minimal as compared to daylight or sunlight or the black body radiator. And the outputs of the project here, we saved around 85% on energy consumption. Let's say 100% in color quality, because the previous situation was too bad. So the color quality improved a lot, and the art preservation we improved 44%. So it's not bad results. Now this project is coming to an end this year, and if you visit the Sistine Chapel, you will see that, and if you have visited in the past, you will see a big difference here. So just as a conclusion, it is a very general presentation, but what I want to say is that we have been centered here in efficiency, all the developments in LED lighting. This is very important, of course, we have to follow this direction, but now we are moving from the, let's say, the green bulb to the brain bulb, because all the lighting is taking is giving more importance to the human being, and has to be respectful with the biology of all of us. So that's it. Thank you.